Okay, I think we'll give people maybe 2 more minutes to join. We can start a little early. Usually we seem to be running out of time towards the end anyway. So here's the agenda for today. Just one section, the sequential allocation from volume 1, chapter 2. And mostly it's pretty straightforward from what I read. I made like one pass through it before. But there's, definitely a couple of subtleties that are nice to appreciate. So, and then there's an algorithm for working with multiple stacks. I think it's specific to stacks. So if you wanted to maintain more than 2 stacks, let's say you had a pool of some kind. So how could you do that efficiently? And there is a little bit that we will need from the MMIX supplement, just a very short piece of code that that I think refers to what Knuth calls indirect addressing. Like if MMIX had indirect addressing, what would it entail? Or what you could do in MMIX right now to do that kind of addressing. And I think Arthur has brought up this topic before as well, so we'll probably look at that. And I think there's a couple of exercises related to that as well. So if we have time, we can try those. Yeah, anything from any of the last sessions that maybe we could review after the break, possibly, or yeah, if anything comes to mind, just bring it up. Otherwise, we can start. So everybody's familiar with the process, so won't spend too much time on that. And let's just begin with TAOCP Volume 1. It's pages 244 through 245. And we'll have about 5 minutes till about 2:13. Hi, James. We are in the middle of reading. We just started a minute or two early, so you can jump in whenever. Yeah, it's great. Okay, would like to summarize what we just read.
Well, I guess I could give it a shot.
Thanks.
And I actually, ironically, overflowed what we were supposed to read. So this is sort of a callback to what we were doing at the very beginning of last week, I think, where I had to go back and look up what he meant by LOC of something, where that's his notation for address of like, where is the location in memory of the jth element of list X. And he's saying that the simple way to do that is you just put them sequentially in memory, what we would call today an array. And he says it's obvious and well known. And it is useful for representing stacks, because with a stack you just have one fixed bit and then you expand out this way and contract, and it's an efficient use of space. But if you're representing a queue, then you have a problem, because you can start putting things on the front and taking things off the back, but then your list sort of moves through memory, and you end up eventually stomping over other things. And so then he's describing a what I would call a circular array or circular queue of, or ring buffer, where you fix a certain amount of space you're allowed to use, and when you go off one end, you come back in on the other end, and then you can store. You can use that as much as you want temporally in time, but you have a fixed maximum space. Whereas the other one, you have an unbounded maximum space, but if you use it long enough, it migrates off into some other piece of memory, and that's not good.
That's fantastic. Yeah, there was another point that he made towards the bottom of page 244 about something being wasteful. Did somebody pick up on that? And if you could just explain that. How is it wasteful for a queue? Or how could it be possibly wasteful for a queue?
Well, what I got from that, which I'm interested to know if there are other interpretations, but to me, that's just implicitly assuming that, as I said, like the amount of memory you're using might stay about the same, but the longer you use it and push things on the front and pop things from the back, the more it's migrating off through space. And he's implicitly assuming that you're not doing anything else with the remaining space. That once you've allocated, byte 0, the bytes in use are migrating off the end 1 to 1,000 to infinity. But you're still hanging on to all this memory, and you can't use it for anything else.
Oh, I did understand that. I actually thought that it was what you said earlier, that the algorithm itself runs out of space to add more, even though the other stuff might have space. The queue itself might not. Like, you run out of like the linear. That's what I understood. Maybe it's what you said. But I thought it meant like about the queue itself, that you cannot add one more because you run out of your max number. That's what it got.
Yeah, Miguel, you're right. Like in terms of what Arthur had first described, that's absolutely right. But I think that this situation that's being described at the bottom of page 244, this is referring to another inefficiency or another potential issue. And note what he says: if R always stays ahead of F, then this is terribly wasteful of storage space. So to me, what it meant was that if we have a use of this queue in which we're not emptying the queue, right? Then what's going to happen is that we are sort of pushing out that initial portion of the queue. Not the initial portion, but the rear portion of the queue, I guess, in some sense. And then, there's these slots that are not being used anymore. We're just sort of adding more stuff. We're not completely emptying the queue, so F never becomes equal to R. And, we're left with these empty gap, actually. That's my understanding of what he was trying to say in terms of waste occurring.
Right. I mean, that's what I think so too, but I think that he's implicitly assuming, without stating it, that you're not using that space for anything else, which I think is true. Again, like I think as programmers, we would say, yeah, of course.
Can you use it? I mean, if you've got this fixed base.
I mean, if you're no longer using X1 because, you've popped a couple times, now nobody's going to use X1 again. I mean, you could, right?
I see what you're saying. So you're saying if we had some kind of dynamic allocation that is giving us these slots and then taking it back when it determines that it's never going to be used again, then that would be one way to address. But I think, yeah, you're right. Like there's this assumption that there's a naive algorithm where, you've just started from some base and then, you've just got these 2 pointers, F and R. And that's the entire region that has been dedicated to this queue.
Can you explain a bit more why you wouldn't be able to use X1 if F moved? So if you increase F, and the queue is no longer looking at what X1 was, why can't something else just say go to that address and put stuff there? Why will be preserved?
Right. I think that is the assumption, and in practice, like these days, like if you are programming in like C or a language like that, that's a very reasonable thing to assume, because in C you have to ask for a memory block of a given size, and then that's yours, and there's no way to give back a piece of it. There's no way to say, because this has been abstracted now. We have a library that you ask the library, you say, hey, I want to malloc some memory, I want 1,000 bytes, it gives you 1,000 bytes, and then you say, now I want to free that 1,000 byte block. And that's the only interface that you have to the memory subsystem.
But isn't the whole point of, oh, sorry.
There's no way to say, I'm done with the first 10 bytes, you can have them back, but I want to hang on to the others for a while. If you had an API like that, an interface like that, then I think Knut's point here might not make as much sense.
Yeah, but we don't have any. So I think the whole point of the MMIX or whatever is to not have those magical things that save you, right? So
I think it's building up to it.
I have his word. At this point, anything can just reserve that, just take your memory. Like, it's up to you to not screw it up, right? Or
I would not put it that way. To me, it's more like he's laying out these building blocks. He's saying, okay, this is like the very simplest, most naive allocation scheme that you can come up with, the most straightforward, and with these assumptions that Arthur is describing. And then he's going to build up to other schemes by pointing out the weaknesses or the deficiencies in each scheme. And so, so let's go on to the next possibility, which is this circular.
One more thing has occurred.
Sorry, go ahead.
One more thing has occurred to me while we were talking about this, that something else that might have been in Knut's mind here is, even if we assume that this is, he does say wasteful of storage space, so probably he does mean he's holding on to the storage as this stuff moves. But as your queue gets bigger and bigger, the indices that you are using to index into the table are going from, like, R equals 1 to R equals 1,000 to R equal, you run it for a couple days and now you're in the millions. And these are big numbers, and they take a lot of, eventually you're going to overrun the size of your word, and he's operating in a decade in which the words weren't that big. And, maybe you want to avoid any kind of scheme that results in big numbers.
Yeah, that's actually another interesting point. In other words, the offset, if you were more judicious about, using the least amount of space that you actually need, then the offsets are not going to grow. And so if the offsets don't really grow beyond what you really need, then you become independent of where that region is in some sense. Is that what you're pointing out, Arthur?
Something like that, yeah. Okay. That there's a benefit to being able to put a hard bound on the size of, not just like the size of the block that we're using, but the size of the indices that we're using to point into that block.
Okay.
It's just bound everything.
Let's move on to the next couple of pages. So this is just right where we left off. And then, where he's given the specifications. So just below that, continuing to page 246, and there is a little bit towards the end of page 246, for which, if you get a chance, open up the MMIX supplement, and there's an equivalent code snippet on page 17 of the supplement. Okay, I tried to simulate what Knuth may be talking about when he talks about wasteful of the storage space. And I pasted that into the chat. I think I got M wrong. M, I think, is 3 in here. But that's sort of the idea that I was trying to explain, that if R stays ahead of F, then we end up with these empty slots behind F. And we'll never set F to 0 because that only happens when F equals R. And so as Arthur said, if these are, like you've gotten a whole chunk of memory that's just associated with this particular name or this particular queue, then nothing else can use it. Okay, so regarding what we just read, overflow and underflow, somebody want to explain that?
This section was about, in my reading, this section was about the problem of multiple stacks. So you could, if you had just 2 stacks, you can use the space more efficiently by letting one grow backwards. So you have one set of memory, and one can grow backwards all the way, and the other one, or the other one can grow forwards all the way, and you don't have any wasted space. But then what happens with 3 or more stacks, and at that point, he's talking about moving the base of the stack, which means moving all the contents of the stack as well, like with some kind of memory move operation. Is that not the? I didn't see anything underflow and overflow, or at the top, I guess. The usual policy in the case of overflow is to report reluctant. Underflow is, oh, I get it. Underflow is probably not an error condition. It just means there's nothing left in the stack to take. Overflow means the stack wasn't big enough, and it's probably an error that means you have to stop.
Yeah, I think you got everything. But yeah, the overflow and underflow piece, which is kind of short, but that's at the start of the section that we were just reading, where he's just explaining that these are 2 conditions that you'd need to be aware of, and you'd need to handle somehow, decide what to do. And then, yeah, he does go on to the case when, because it's sort of related to overflow, right? It's sort of like saying, if you just have one list, then yeah, with overflow, you do have a problem. But if you have multiple lists, then it would be nice if you didn't have to report overflow for a single list unless your region of memory that you've allocated for multiple lists has actually run out of space. So that's, I think, the initial description that you provided, Michael. But if somebody else has another take on it, please go ahead.
You did use the word the region of memory you've allocated, and I am positive that here, when he shows this diagram, he means the memory. This is what my memory looks like, and I have some fixed size tables maybe at either end, and in the middle I have the 2 lists that happen to be in memory while my computer is executing its program. This is as old school as it gets, right? But he does.
Don't you think that he, at least in that initial where the lists are growing towards each other, he's assuming that is a contiguous region of memory?
Well, yeah, the computer's memory is contiguous. But he's
saying that he's just referring to the entire memory?
Yes, these are the 2 lists in your program, and as long as you only have one.
Does it have to be? Does it have to be? Like, wouldn't this work from? Couldn't this be applied to just what I was describing, which is a smaller block of memory, not the entire?
Yeah, I think it's a smaller block of memory. I think it's whatever memory you allocate. He says above 1,000. He doesn't say that the front stack is at byte 0 or is at address 0, and the end of. Well, he says end of memory, but I don't think by end of memory, I don't think he means 2 to the 63rd or 2 to the 64th minus 1.
Well, I think
he means the end of the memory allocated for that structure.
Memory to use.
The memory allocated is the universe for this program. So that's the computer. That's
But he's saying this works great if your program only has 2 lists in it. But where does he talk about you might have 10 or more and then you're in trouble?
So that's the part that I really want to understand.
For a program to have 10 lists in it.
10 stacks, not lists, stacks.
Wait, but
lists.
But hold on,
Michael, I think Arthur is right. It's a little more general. he does give a special case for stacks later on, so you may be remembering that. But I think initially he is describing multiple lists.
Yeah, he says, this is on page 246, when there are, say, 10 or more variable size lists, and this is not unusual, the storage allocation problem becomes very significant.
But
allocation.
Can you guys explain something before we continue? What I understood is that he means using this technique to have like one conceptual list divided in little chunks to handle the memory allocation. So that what I understood is this is a technique for you have like one list in your program, like conceptually, and you are dividing in a bunch of little ones. That's what I understood. So that's what I want to understand. If that's not what he meant.
No, that's
he means like in general
one
you
way
have
you can
different
look at it. But what he's describing is multiple applications. So you're doing different things with different lists. You don't have just one list. You're not dividing up your application use of this data structure within just one list. You're not creating a smaller sub list. You just have different lists. You're maintaining different lists for different reasons, but they all have to live in the same memory. So
I get it. So that's why A and B cannot be at the same time. Makes sense.
I'm sorry.
Now it makes sense. I didn't understand why you couldn't keep the bottom address fixed. Now it makes sense. If your lists are growing, you need to you might have to move one list to make space. Right, that's the problem.
And again, if we're thinking of this in 1950s, 1960s terms, the idea of a computer program that has a list of things makes sense. If you're thinking in the this decade terms of like, well, how do I write a web browser with only one list? The answer is you don't. You're going to have 10 or more lists in your web browser.
10 or more lists per tab.
Maybe even multiple lists per tab.
Yeah, many lists. Yeah, so again, this is how I see it. Like he is really just building up this groundwork for more and more sophisticated uses of memory. And so he gives this two list scenario first, and then he's saying, oh, what if you had more than two? And he also says that once you go beyond two, then this simple allocation scheme is not going to work for three, and so then we have to come up with something even more general. By the way, this the two list scheme that is illustrated on page 246. This exists and I've mentioned the GNU sort program before, where I'd seen references to TAOCP. And in GNU sort, if you've used the sorting program, it sorts lines by default. And if you look at the way those lines are represented in GNU sort in terms of data structures, what they do is they keep the raw line, the string of bytes, in a list that's growing and shrinking depending on how many lines need to be sorted and merged. And then at the same time, they've got another list, which is sort of a marked up or a data structure that somehow represents that original line. And they've got another list of that. And these two lists are stored in one contiguous region of memory, and they're growing towards each other. So there's the list of the raw lines from one side, and there's a list of the other representation, sort of the object representation of the line growing from the other side. So I found that really interesting, and not sure whether they got it from here or it was just like something that was well known. Okay. I think that's about it for this section. Let's move on. The next section, there's a little bit more involved here. So we continue on page 247, and then we go on to, I think it is the middle of page 248, just before the algorithm begins. Okay, so the diagram on the top of page 248, where it represents memory after several insertions and deletions. Could somebody walk us through that? The sequence of operations are just below that figure 4. However much you've understood, like we can just start with the first operation, explain what we're seeing, and then maybe somebody else can continue.
Well, I can give it a.
Thank you.
So, where do I start with this? He's saying, what if we have a whole bunch of lists, but a fixed number of them? We have, I think, n stacks.
So we've got 4 here.
Yeah. And the values base sub I and top sub I are the base and the top of each individual stack. And so we have registers or variables somewhere with base sub I and top sub I in them for these 4 things, for these 4 stacks. And they all initially start at 0. And then we start adding elements to these stacks, and we basically start them all with size 0 all on top of each other, and we can add then the first element basically for free, and then we can add another element to that same list also for free. But now suppose we had to add another element to one of these size 0 stacks that was already there. That would overwrite our existing element, and that's not allowed. So we can detect that issue and say, okay, well, I'm going to bump this list down over here in memory. And then I can start adding to it. And if I need to increase the size of the first one, then I will just pick this list and move it a little bit further over so that I can move this, so that I can make this one bigger. And by just slightly shifting each list and sort of bubbling them up and down in memory as I need to, I can end up using my memory efficiently for a large number of lists with horrible, horrible efficiency, although he doesn't say so.
Right, yes. You're trading clock speed for memory, which is, back in the 60s was important.
And so allegedly, the configuration shown in figure 4 is what you get after doing this sequence of insertions and deletions. I'm not sure that I followed it exactly. I guess one thing about the algorithm that he's using here is that he's always keeping top of k less than or equal to base of k plus 1. So no list ever leapfrogs over another.
Yeah, and as long as we can do that, we're fine. But at some point, we may not be able to do that.
Right, and that's when we have to either bubble the bigger ones up, so bubble the greater, what would we call these lists? The ones with higher addresses, we're going to bubble them up, or bubble the ones with lower addresses down, if that is possible.
Okay,
and
so
or we have to add an algorithm so we don't know when we choose to bubble down versus bubbling up. But it's fact that as soon as we get to the first algorithm G here, he's already gone on to a better algorithm anyway.
Right. So yeah, so if we just look at that sequence, initially base and top of the 4 stacks are these are stacks, right? I don't think this works for arbitrary lists. So these 4 stacks, base and top, are all at 0. And then we get the first insertion into stack 1. That's what I1 is.
If I could,
yeah.
One thing that a very similar thing ought to work for decks. There's no real, there's nothing that limits us here other than the names base and top. If we just rename them to front and back, this should work fine, even for doubly ended things.
Okay, you'd have to show me how to do that. I am not, off the top of my head, I'm not quite seeing, because in this case, you're always going to be removing from one end for each one of those stacks. And the base is not, yeah, I'd have to work it out, but you may be right. Anyway, for stacks, after the first insertion into stack 1, or on that first insertion, we're going to get an overflow. Right. So then
the reason we're getting
go ahead.
already there is that stacks aren't allowed to leapfrog each other. If they were, we could just say, okay, I decree that this first element goes in number 1, leaving stack number 2 and stack number 3 and stack number 4 all still at offset 0. But we're not allowed to do that. As soon as we've got something in number 1, we've got to move all those other stacks up to offset 1. Or I guess he's calling it offset 2 here. One based indexing.
Yeah.
So inserting into number 1 is always going to cause overflow here. And then we insert into 4, and because that's the last one in our set of stacks, we can do that without overflow. There's no list 5 for it to bump into.
Right.
And so that doesn't have overflow.
Right, exactly. Yeah, so with I4, which is the third operation, is the last stack, and so there's no overflow and there's no need to adjust these other stacks. And then with D1, we're going to go back to stack 1, and we're going to remove the entry from slot 2, because that was the last one. What happens at that point? Do we need to do anything? Do we need to adjust anything else?
Just top of 1 gets decremented. That's how top of 1 got from 3 to 2.
Just top of 1, which is obviously required for the deletion. So yeah, because right now we're not actually, so anyway, with I3, we've now trying to insert something into stack 3, but stack 3 is still at 0, and so we hit overflow here. What do we do with stack 3? It's not allowed to leapfrog over 4.
Yeah, what happened was you don't get I1, the very first I1 for free. What happens is when you put in I1, base of 1 stays alone, and top of 1 is going to be pointing at 1, and all of the other ones are going to move up.
Oh yeah, that's right. Base 3 has already moved up, so it's already at 3, right?
Yeah, the only one that you get for free is I4, because base of 4 and top of 4 are at the end of the list.
Okay, so when we do that first insertion into stack 3 and we do get overflow, what is base of 3 at that point?
I think Michael's right. I think it's 3, because we've inserted 3 things at this point.
Okay, so what happens at this point? Base of 3 is 3. We have overflow. We need to move stack 4
the only thing that's
up, right?
The only thing that's overflowed, though, is base of 4. Base of 4 is in the place that we want to put whatever we're inserting on 3. So we've got to move just base and top of. Base and top of 4 get pushed down 1. There's no data in that stack, or is there at that point?
There is one element,
There is one.
so we'll have to copy that one element in memory up.
Yeah, so that has to be pushed down, I think. Yeah, sure.
Yep.
Okay.
If anything had been taken off of 4, then we would have a cell ready, but it's still not for free because we're going to take base and move it.
Okay.
No, I'm not sure about that.
Well, we have to modify the values of base and top of 4.
Exactly.
And then we also have to move in memory. We have to move the contents of base of 4.
Even if the stack is empty, if there's stacks beyond where we're trying to insert and we've run out of memory, we have to move all those bases and tops down one spot in memory. So,
right.
So the first insert at 3 is not free because even though stack 4 is empty, in the middle that you have that I3 with a star by it, that wasn't free. The star means that it had to move things down. And at that point, stack 4 is empty, but we still have to move base and top down for stack 4.
Okay, Michael, can you also maybe explain the slight optimization that he has towards the end of that reading where he says we could eliminate the first stack overflow for each one of these stacks in a certain way? What is that formula saying?
By setting them all to sequential places in memory?
Not sequential, but evenly spaced. He's
evenly
saying,
spaced,
we,
and that
we know we have this much memory, we can just space them out and
right.
say, I'm going to assume that they're each going to take roughly the same amount of memory.
Right,
and
right.
only if one of them actually takes that much, then I might have to take the other one, however much space it took, and I might have to shift it down. Or, yeah.
Right. So if you had 4 stacks and you had 10 cells, then you could have base and top of 0 would be 0. Our base and top of for the first one is that, does he call that 0? No, base 1 and top 1, you could set that to 0, and base 2 and top 2, you could set that to 2 or 3. I picked a bad number, 10.
Yeah, just divide by 4 and
divided by 4.
2.5 and then the floor of that.
So you get 2 and 5 and 7 instead of all at 0.
And if your
then you
data
get the first couple of inserts in any stack for free.
If your data is nice, then maybe you'll never get an overflow, right? So if your processing and the sequence of operations is reasonable, then maybe you don't get any overflow at all. So the formula then looks a little nicer now. Does everybody agree?
The formula?
The formula, page 13, where it's basically taking that average and then adding a base offset to it and coming up with that starting point for the base.
You're talking about number 13?
Formula number 13, right?
Yeah. And also
that's more complicated than it is.
Yeah, I mean, my first reaction was like, well, really all he's saying here is that if you allocate the right amount of memory up front, then you won't have to reallocate. And I was like, yeah, I mean, duh, right? Like, of course, if we're willing to use all of our memory and just say, well, I'll just allocate 1 million bytes for this thing, and then I never run out of memory. Like, awesome.
No, but I think he's saying that this is some block of memory that's meant for this pool. That's why he's called it L infinity. It's not, the last slot of 2 to the 63 minus 1 or something like that.
That's the way I read it.
So is that L infinity the equivalent of the base 5 in the figure?
L infinity would be 20. Yeah, 20 or 20. Yeah, he's actually got that. He's got it labeled on that figure, just below the figure.
So it's basically like a helper, like this is the end. Like this is all the space for all the stacks. Is what I understood.
Yeah.
So it's really L first and L last.
Yeah, essentially.
Would have been a better way of notating it.
For sure.
Okay, nice. So we're just a little past 3. We're doing well on time, I think. When we come back, we'll have a break, 10 minutes. When we come back, I was thinking maybe we can try a couple of exercises before we continue on to the algorithms. But yeah, enjoy your 10-minute break. See you. Hello. We're back, and I thought we could look at a couple of exercises before we go on to algorithm G and R. So the first one that Knuth recommends is exercise 1 at the end of the section. And all that's asking is how many items can be in the queue without overflow occurring. This is sort of the simple case. It's referring to page 245.
In particular, there's somewhere in here where he says that for 2A and 3A, for the stack things, the answer is M.
Mm-hmm. And
but the answer is for a queue.
Yeah, what is the answer for a queue that's specified in 6A and 7A? What's the maximum number of elements that we can store? Is it M?
Well, I don't want to be the one to spoil it. But it's not M.
Well, it's an exercise, so we know that it's probably not M. Michael, are you saying something? You're muted.
But why? What's a good way of convincing yourself that you can't have M? I mean, the answer is because when you have M, the top and the bottom circle around to the same thing, circle around to the same index, so you can't tell the difference between an empty buffer and a full buffer. Is there any other way of looking at it that makes it seem simpler?
I think that's what it is. That's the key thing, is that F and R are no longer 0. We're starting with F and R equal to 1, and then because of the way the overflow detection works, we need to have that extra slot.
Well, you can actually have M elements in the buffer if you allow, if you index them from 0 to if you index the buffer from 0 to m-1, if the only thing you ever did was insert, then, and if you allowed the end pointer to go up to m instead of m-1, that's one case where you can actually have a full circular buffer. But as soon as the F and the R are pointing to the middle of the buffer, there's no way to tell. Do you get what I'm saying? Do you get what I'm saying? If, let's say you have 10 elements in the buffer and you start with F, what are the letters? F and
R for the front and the end. Yeah.
Okay, so F and R start at 0, and you fill in you get 10 inputs, so you fill in the memory locations from 0 to 9. If you let R be 10 and adjust it when you take something out, then 0 and 10 mean the buffer is full. But that only works if you haven't taken anything off of the front, because if you start by putting one in and taking one out, now F and R are 1. And now if you put 10 elements in, you get up to the 9th element, R is 10, and we put one more element in. I can't put something at 10, so I adjust R from 10 to 0, and I put the element in at 0. I can't tell the difference between that and an empty queue.
I reject the notion with him being so space efficient that he has an algorithm which is forced to waste one cell.
Well, if you have one extra bit of information, like the extra bit of information would be that the last operation was a put, then you could tell too. You could let it be. You could use that last cell.
So I feel like the point here is not that you can't do it. The point that is that the way he specified it, which is a relatively simple algorithm, you know, you just increment. If you hit this boundary condition, then you reset. So with that sort of logic, you need this extra slot. But if you really wanted to use all of the slots, then your logic would get a little more complicated.
And actually, if the slots were only a byte, only a single unit of information, any way that you would do it, even the algorithm that I said where you could let it fill up if it started from the beginning and went to the end, you still have one extra bit of information somewhere. So you're allowing the buffer to be full, but you got to keep an extra bit of information to say whether or not that last operation was a put or whether or not you're at the beginning. So in the simplest case, the buffer can only have m-1 elements in it.
Okay.
A circular buffer.
Okay.
I think that's the way circular buffers are in general. I mean, in Java, I think that's the way it is. Not sure about it, but
I think if you do it, and if you look at like the information theoretical, you know, like how many bits do you have available, and you count up how many states can my queue be in, and then how many bits do I have available in F and R. I think you can work it out. I think basically, what do you want to do? You just want to have some combination of F and R that's like, you agree that it will never be in this state unless it's full, and then I don't know. Anyway, this is certainly a digression exercise.
I don't know whether that holds. I can imagine some complicated algorithm that'll get that extra bit out of F and R by not having them actually be the first and the last byte.
Well, yeah, I think in practice what you'd want is F and size. So F is like, where is the first thing? And that can obviously range over the entire array. And then you have size, which can be 0.
If you have F and size, then you can fill it up.
No, I mean, if I had...
If size is 0, it's empty. Size is M, it's full. You can tell the difference.
But I can't represent M, right? If I have, let's use bytes for the example. If I have an array of 256 bytes, numbered 0 to 255, and then I have another byte that can hold the size... I can say I have 0 elements, or I can say I have 255 elements, but I can't say directly that I have 256 elements.
Yeah, you're cheating.
But every 0
you got
element...
a boundary case there. You got a boundary case.
Well, information theory is all about boundary cases. If we assume we can represent every number, all the problems go away.
Yeah, it's really the boundary case where, you know, he's trying to simplify that boundary case, at least in this version of sort of the initial algorithm. What about exercise 2?
Okay.
It's asking for us to generalize this method that we just were talking about so that it could apply to any deck with fewer than m elements. So in other words, give specifications for the other two operations, delete from rear and insert at front. So 6A and 7A are specifying a queue. And as far as I understand this exercise, it's asking us to do something similar for a deck.
This seems like the sort of thing that intends you to work it out on paper, because I think as we're just talking it out, it's like, well, of course you can do it. Just subtract 1 from R instead of adding 1, and that gives you pop from the rear of the queue. And if R is F, then overflow. and it just seems intuitively like that's fine. Writing it out, I think, is the point of this one. And similarly, to insert at the front, you just subtract 1 from f. And then if that made f equal to 0, then set f equal to m.
So how would that be different from what is already in the queue? For the queue specification? So all the steps, like, okay, so for the first one, which is delete from rear.
So delete from rear would be basically 6a with a minus sign in it. Yeah. Maybe I should type it out too.
Yeah.
So delete from rear.
So let's take the boundary case first. So
Same thing. If f equals r, then underflow. It's more like 6b, or 7a than.
Sorry, yeah, it is 7a. It is 7a. Yeah.
7a, but delete from the other end.
So if r, no, so wouldn't it be the same? If f equals r, then underflow?
Yeah, that would be the same. That step would be the same. But
and then the second thing would be
if r equals 0, then r equals m. Then put m into r. Because we're gonna put it on the r end, not on the f. We're not gonna put it on the front. We're gonna put it on the back.
No, we're deleting.
Oh, right.
We're deleting.
Still the same thing. We're looking at r, not f.
Right.
Right. So if r equals m, then r is assigned 1. Otherwise,
no.
R
If
is
r equals
incremented.
0, if r equals 0.
No,
R
I
is
think
gonna
we
decrease.
still want the same initial condition. F equals R equals 1.
R is going to decrease, isn't it? Oh, it's going to increase?
Here is my solution for pop from the
Yeah,
rear.
you're right. It's going to increase. R, we're deleting. I get it mixed up.
So if
Yeah, you're
R
right.
is,
If r equals m, then r goes, then put 1 in r.
if
Otherwise-
R is 1. Okay, so if we've come back all the way to 1,
No, we're deleting from the rear, so r is going to
R minus 1?
R is going to increase.
Yeah.
It's going to follow f. So if r equals m, then r equals 1. Else r equals r plus 1. So it's the second step is the same as the second step, except we use r instead of f. And then the third step, x of r assigned to y instead of x of f assigned to y. Or y, I don't know how to read that. Y from x of f.
And when you write it down, it's got subtle off by 1 errors. But I think this is one you have to write down in order to get the point, because obviously talking it out, it's just like, yeah, you can do it.
Right, right.
I'm not sure about that. I think it's just as simple as that. If r equals m, then r from 1. R is going to be moving forward, except when it gets to the end. Then it's going to go back to 1, because we're taking something off from r.
Right, which means it goes closer to the front.
That's right. When you delete from the queue, it gets shorter, and r goes toward 0.
No.
Yes.
Wait, okay.
That's how math works.
I've got the wrong picture of it then. When you put something onto the stack, F increases and R is 0.
Insert into queue. Well, when you insert something into the queue, you insert it at the rear of the queue.
If insert into queue, if R equals M, R equals R plus 1. You're right. I got it backwards, that's all. You're right. You're right. So
the rear and come off at the front.
So delete from the rear of the queue means that you back up R. So we were
So for a deck, we have 4 cases, right? We can delete and insert from either
when you
end.
say delete from front, what you mean is delete from the queue, right? The way that you remove a person from a queue is you go to the person at the front and you deal with them, and then you remove them from the queue. So what you just put in the chat there, delete from front of deck, that's already been done for us.
Okay.
It was the action of taking someone from the back of the queue.
That's different, yeah.
Abnormal. And likewise, letting someone butt into the front of the queue is abnormal. And so that's the other one we haven't done.
Yeah, so I can just say, yeah, he doesn't even ask that in the exercise. Okay, so then insert into front of queue, front of deck.
So R becomes F and N becomes 0. And F is assigned from F minus 1.
Okay, I think what I wrote is correct. The moral of the story is indexing your arrays at 1 is confusing to modern people.
Indexed from 1. So if F equals 1, then yeah, it has to be indexed from 1 because we're looking from 1 to M.
So Miguel says, can you explain why F mod M? Because we want to do basically all of our arithmetic mod M. That's basically why there's the special case in all of these mini algorithms that says, if we're already at M, then go back to 1, otherwise just go up by 1. That's the same thing as saying, take R mod M and add 1 and put that result back in R. So here, what we really want, instead of F mod M plus 1, another way to say that would be the previous value of F. So another way.
But aren't the arrays indexed from 1? In which case, if that first step fires, then assign F from M, If f is m, then f mod m is going to be 0. Oh, you got the +1. Oh, God.
Mhm.
Like I said, I think this is correct. So I'm writing out an alternative phrasing using a necessary variable.
But you don't need that because
You can do this.
but FM is a valid spot.
No,
X
if f is m, then we have overflow.
He's got a +1 there. So if f is m, then the f mod m is 0, and he's got a +1, and he's taking it from x of 1 instead of x of m.
Right, but
If that's correct, then we're good.
But so we're not going from 0 to m minus 1. We're going from 1 to m. So x of m is a valid spot.
Yes, and sometimes we write to it. Sometimes.
F equals 1.
Well, no, if x equals m, then f mod m plus 1 would be 1, not m.
That's correct. So when is it that f mod m plus 1 equals m?
It never does.
It does if f equals m minus 1.
Oh, okay, yeah.
So what I was doing with the f mod m there, or f mod m plus 1, is just undoing the effect of the if f equals 1 line, because we're trying to write into x sub old f, not x sub current f, but x sub old f. But now we've lost old f. So the alternative that I just put in there at 335 was save off the old value of f in variable o, and then we can write to that spot. And you might say, well, why don't I just write y into x sub f at the beginning of the algorithm? Why do I need to wait to do it at the end? And the answer is, well, if we're in an overflow state, we actually don't want to write y into memory, right? If we're going to have overflow, then writing y would be the wrong thing to do.
Well, you're right. If you're going to have overflow, you're writing into that extra unused cell, and what does it matter? So I think you could just write it.
That's possible. Yeah.
But then, of course, you have the situation where you've done the push, and then said overflow. So if the push is successful, you're not in an overflow state.
Well, you are, because you're. I mean, it really depends on what kind of entities we're dealing with here. You know, my C++ mind is saying, no, this is violating the preconditions of this thing to construct an element and then signal overflow after that. But of course, if this is just writing integers into memory, I think Michael is correct. The whole point of exercise 1 is that we have an extra unused cell at just the right place to make this work out.
But I'm saying that if you have the extra unused cell and you use it, it's not an overflow. It's not an overflow to do another push.
But it is an overflow.
Well, it is an overflow because even though you successfully put the element into the memory, now the f and r are equal, and it looks like an empty queue. So if you didn't have the underflow, then the queue, everything in the buffer disappears.
And you can never get it out anyway.
Underflow, then f and r are going to be equal, and it looks like an empty queue, even though it's full.
Yep. Yeah, I buy this. And the other thing I'm doing when I write one of these algorithms is comparing it to the one in the book that does the opposite, right? So we should have something where if I insert y at the front of the queue and then I run algorithm 7a to delete it again, I expect to be back in the state where I started, unless I had overflow. And it looks to me like this is correct. So we write it at location F and then subtract 1 from F. And then to undo that, what 7a does is add 1 to F and then read Y. So yeah.
But if you add one and delete one, your buffer isn't quite exactly the same because F and R are going to be, what would they be? Would they be 2 or 1? I get the indexing screwed up. F and R are going to advance by 1.
No, we're subtracting 1 from F because we put someone on the front, and then we
gotcha.
And we add 1 to F because we remove them from the front.
Oh, gotcha. This is the deck you're removing from the. Got it.
Yeah.
Okay, let's do the final bit of reading, which is back on page 248. And these are the 2 algorithms which are kind of a different take on that multiple stack problem. And this is being used only after overflow. So overflow has occurred, and then Knuth is saying there's these 2 algorithms that you can use for sort of the alternative to the repacking that he had described before. So we have about 7 minutes to about 3:50. Okay, so as much as we can understand it, somebody want to summarize the basic idea? I mean, we don't have to go through each step, but what's the big idea? How is it different from the simple repacking that was described earlier? James,
I can take
in the simple repacking, we only made space for one element when we needed it. And in this one, we're taking the idea of allocating the memory equally among all of the stacks, except we go even further than that because we're trying to weight the amount of memory that when we need to shift things around, we're trying to weight the amount of free space on each stack by the amount that each stack had grown. So the more active stacks, or the ones that have grown the most since the last overflow, get the most memory.
Michael, if we go back to that figure 4 on page 248, where there's that depiction of memory after a certain number of operations, is it possible for you to maybe explain what would happen with that kind of sequence of operations? How would that memory look differently?
Well, that would only, what's on figure 4 would not really happen because we'd start out with these, well, it could happen, but only after a bunch of things had happened.
Yeah, figure 4 is not going to happen. So I agree with that. That's not my intent. My intent is if we take something like that with those parameters, you've got 4 stacks and that bit of memory, total amount of memory, and then you go through these these operations in that sequence. So we push the first
so if you pushed something, if the state was like 4 and you pushed something onto, I guess, 3, that would cause an overflow, and then the algorithm would go through and it would say, okay, you have 1 plus 2 plus, if I counted it right, 12, 14 cells that are free. And then you have that crazy alpha and beta. You're going to say, well, not enough information here because you would need to know what the size of things were on the last. You need the old.
Right. You do need that. So if we start from the beginning, that very first operation, let's say, we've just got this sort of area from scratch. We're at the beginning, but if we apply that same algorithm G and R, to a memory block that has 20 slots and we've got 4 stacks, we're starting out with some initial conditions and we do that first push onto stack 1. What happens?
So you're talking about all the stacks are empty and you push something onto stack 1?
Yes. Yeah.
Okay. You're going to get that for free because it's not going to look like that figure because base 2 is going to be, where would it be? It would be at 5, I guess, right? You'd have base 2 at 5, base 3 at 10, because you're allocating. So every stack will start out in this figure with available 5 bytes or 5 elements. You want to call them words, whatever. So when you want to put something on, when you want to do I1, all that's going to happen is top of 1 is going to go to 1.
And what about old top?
Old top, it will still be 0. You're not going to touch that old top until you shuffle the memory around. Then all your tops become your old tops, so that you can remember how big each stack was. And the reason why you need to know that is because the algorithm is allocating some memory on the basis of how much each stack has grown since the last stack overflow.
Well, it initialized old top with top. So after the first insertion, old top is top 1. So, no?
Well, before any overflow has occurred, old top is initialized to be the same as top. But when you insert an element into the stack, you're not even invoking this algorithm. Old top still stays at, old top of 1 still stays at 0.
So I'm confused. I thought there was no zeros so
old,
0 means that nothing has happened. Is that I haven't seen a 0 yet?
I think when it starts,
Oh, I see.
it's
Yeah,
L0, L first. Yeah, I'm saying 0, but it's L0. I suppose I should say.
In page 246 at the end it says L0 starts at 0. So yeah.
Yes. So.
This is a long algorithm. Like,
or is it?
I think I would need like a week of exercises and stuff just to really know what's going on.
Yeah, so we want to cut down on that week in the few minutes that we have. Whatever we can do. So yeah, so one of the key differences is this unequal or weighted allocation of memory. So there's 10% of the total memory. So if we had 20 slots, so we would allocate 2 out of that 20 to grow. Yeah, so maybe 20 is this is not really that useful for that few number of slots, but let's say we had 100, right? We had 100 total number of slots. We've got 4 stacks. So when we do hit an overflow, we're going to allocate 10 slots.
So a good case to consider might be you have your total memory is 100, and you have 4 stacks, and the only thing you ever did was you pushed 25 and then pushed 25 onto the first stack, so that fills it up. And then when you push another element onto the first stack, now you need to move things around. Even though the other blocks are memory, even though the other stacks are empty, you still need to move things around. And what you get is that the other stacks don't really, the first stack has grown by 25, and the other stacks haven't grown at all. So you take 10% of the available memory, which is 75 bytes or 75 words, and you add 7 to each of the other stacks, but the balance of the memory, that you're going to add goes into stack 1. So you make most room for stack 1, which has grown by 25 elements.
No, would it not be the next stack? Like initially you said stack 1 had grown to 25, and then we are trying to insert or push something onto another stack, right? Stack 2, for example.
Well, if you did that, then there's no overflow.
There's no overflow there.
But so you don't invoke this algorithm. What I was trying to do was I was trying to make it simple and saying, okay, we didn't push anything onto the other stacks 2, 3, and 4. Mm-hmm. So their old tops equal the tops.
Right, so let's finish that example. So now we have an overflow condition on stack 1. And so the first in algorithm G, G1, G2, and G3 compute that sum is 75. Because
how do we get an overflow condition on stack 1 with just 25 elements if no other stack has used the memory?
Because
we used equation 13.
We would have to put it into 26, which is the memory reserved for stack 2.
Oh, you're assuming. Oh, I see what the disconnect is. You're assuming that we've got the even, uniform initial.
Exactly.
Yeah,
exactly.
I was going with everything at 0. I wasn't assuming that initial distribution at all.
And we're not using the algorithm for 248. We're not moving the stack pointers, the base and the top around in that simple fashion. We're just at the point where we've detected the overflow. What are we going to do with all these bases and tops and with this memory? And instead of just moving like the algorithm on page 248 says, okay, it's pretty simple. You just move base of 2 up by 1, and it becomes like I1 star. You're not moving any memory. You're just moving the base of the next stack over to make room by one element. Instead, we want to make it so that each stack has the most memory that we can reasonably assign it. And what we also want to do is we want to assign more free memory to stack 1, which has had 25 elements stuck on it.
Yeah,
the other stacks have been idle.
I'm sorry to interrupt, but I'm not convinced that that's our starting point, because he's referring to equation to whatever you want to call this, number 9 on page 247, which is just simply saying that you have n stacks. That part where we have this different uniform distribution as the initial state, that's something else. We could start from that too, but we don't have to.
Right, but we are going to, because equation 13 says that we should. So we're going to do that, and then we're going to work through the rest of this example, right? So we're trying to push the 26th element onto stack 1. So what happens at this point? What happens is we compute sum using steps G1, G2, and G3. Sum comes out to 75. Then we're going to take a 10th of that 75, and we're going to split that, so that would be 7, and we're going to split that evenly among our 4 stacks. So we're going to give 7 over 4 is 1 word of memory to each of our stacks. Now remember, the last 3 have 0 elements right now, so we're allocating them room for exactly 1 element so far. And then we're doing the other 90% of that 75 proportionally to how much they have grown. So how much have each of them grown? One of them has grown by 25 elements. The others have grown by 0. So the one that's grown is going to get all the rest. And the ones that have grown by 0 are going to get 0 of the rest.
Okay.
The rest is, we gave 1 byte to each. So that's 4 bytes. That leaves 71 bytes left that haven't been used. And we're going to give all that 71 bytes to list number 1. So, which also has size 25 already. So that's a total of 96 plus the 1 we gave it out of the 10%. So that's 97. And so our final distribution of memory is we're going to immediately give 97 bytes to number 1. And we're going to bump the other 3 lists down to have 1 byte apiece.
Yeah.
1 word apiece.
So then what happens when one of those other stacks has 2 pushes in succession, for example?
On
the second suite, yeah.
Okay, so at that point, and we're assuming that there were no other insertions in the meantime. So let's see, how am I going to write? I'm trying to figure out a way of like notating this to make it make sense. Let's say that after the, here we go, and working, buffering. So then we put 1 element in that one, and then these ones still have 0 elements. Okay, so what I just put in chat here is size and capacity of each of these stacks. That we start out, we give them each equal capacity. And then we do a reallocation. And then, well, I guess really I've already made a mistake because the overflow in the first one was caused by adding a 26th element. So really a 26 elements in the first one, 1 element in the second, and no elements in the others. And so now we have an overflow condition on the second list. So how much unused memory have we got here? Looks like 70.
100 minus 27.
Minus 1 minus 1, yeah.
73. 73. Yep.
73. So again, 10% of 73 is 7. Yeah, I feel like this part of it is never really going to be that interesting because we're going to give 1 byte to anyone who hasn't grown. But now someone has grown. Oh, well, this is just like the awfulest case possible, right? Because now the first list hasn't grown at all. Its old top and top are the same, yes? And so the first list is going to get 1 of those bytes. The third and fourth lists are going to get 1 of those bytes, which they already have, which is fine, and that's actually what we want.
Hasn't the first one grown by 1 for the 26th? It wasn't like old top from before that was added?
That's a good question. Maybe? Set old top j, go to top j for all of them. Yeah, I think, okay, the first one has grown by 1, and the second one has also grown by 1 then. It's about to grow by 2, but it hasn't yet. So we're going to split evenly between the surplus that we have available to us now is the 73 that we had minus 1, 2, 3, 4. That leaves 69, and we're going to split the 69 evenly. So that's 35 to one of them and 34 to the other. And so the final distribution is something like that. Yeah, that looks much better than what it was going to be if we didn't set old top before doing the increment.
And 2 would be, the second list would be 2.
Yeah, the second list would be 2.
Yeah, and then after the insert, yeah, it would be.
Okay, so then we keep, let's say that we keep pushing on to 2, 3, and 4, and then at some point we're going to leave stack 1 with just one word. And then if we start pushing to stack 1, will that even happen? Like, so we've got 60 right now.
Yeah.
I'm not sure I follow.
If you push onto stack 1, it's not going to cause an overflow until you get up to 61. And then when you get up to 61, it's going to try and allocate most of the free memory to stack 1 because that's the one that's grown the most.
No, but what if the capacity for stack 1 keeps decreasing down to 27?
The algorithm won't decrease anything until an overflow occurs somewhere else.
Right.
Yeah, that's right. So we have room to grow, but we can easily do that. We can just alternate between the different stacks, right? We can easily find a pattern that will keep on overflowing every single push.
Right. Now, also,
but we will never reduce the capacity of any stack below its size.
Right.
Yeah, I'm just asking what will happen at that point when we finally decide to push something onto stack 1 and its capacity has gone down to 27, I think, or 26.
Right. Well, then there'll be an overflow, and then we'll just do this algorithm again, and we'll give it some more memory.
I was just wondering if we could come up with a scenario where a stack is forced to move down.
One thing that would happen is if it was 26 and the capacity was 26 and you pushed one thing onto it, it's not going to get much more memory because it only grew by 1. And presumably something else grew by 20 and it's going to, the something else is going to get a lot more memory. So it allocates, it splits up the free memory and gives 90% times the amount that the stack has grown, and 10% is divided evenly. So everybody gets some. And the next, in the state that it is here, stack 1 has 61 bytes. Unless it keeps growing, it's going to lose bytes the next time the algorithm is run, because
I mean, it already lost some. It went down from 97 to 61.
Yeah, that's what happened the first time. It went from 97 to 61 because nothing happened. It didn't grow any.
Yeah. Okay, we're at about 4:15. Do you want to finish up the entire section? There's a little bit of analysis at the end, or shall we skip it?
I already skimmed it somewhat. I
okay, so then let's do it.
A title in the chat.
Okay.
It says that there's a paper by D.S. Wise and D.C. Watson on the further study of algorithm G, but I was not able to find an actual copy of that online anywhere. Not unless you want to pay a Springer link for a subscription.
Yeah, this is before Archive came about, so they suggest working with pairs of stacks that grow towards each other. So we would split up the 4 stacks into 2 pairs, and then maybe apply something similar to that paired region. I think maybe that's the idea. But what is the analysis then, Arthur? What could you maybe just let's spend maybe 2 or 3 minutes just reading it, and then we can discuss.
Sorry, reading what, the rest of the chapter?
Yeah, the rest of the chapter. This is page 250 to the end of the, not the chapter, but the section.
Yeah, no, yeah, that's the epigraph, I don't know how to say that. Yeah.
I love it. Only Knuth would come up with these problems.
Which one are you talking about?
All of these things in general. It gets it's so much into combinatorics. Like we left off last week talking about inserting and removing from a stack. How many different possible ways was there to do that?
The valid sequences, yeah.
How many valid sequences? And it turns out that it's actually not that complicated. I had most of it figured out in my head that you could do it by those strings of S's and F's. So if you have n elements and you want to figure out how many combinations of S's and F's, that's pretty simple. That's the number of 2n things take n. So it's 2n over n. You know, number of permutations of 2n things taken n at a time. But you have to subtract from that the number where you do an underflow, basically, where you try to extract X something out of the stack that isn't there yet.
Okay, maybe next time we can go into that like in more detail. If you write it up, and then we can definitely look at it. That would be great.
It was interesting. The answer in the book, I looked at the answer in the book for the end. I just didn't quite get that last step, and he's got a really long answer in the book, but the answer to the problem he answers in the first paragraph of that answer. Then he goes on in the typical Knuth style and poses a more difficult problem.
I must return to my day job, so I'll see you guys next week.
Thanks, James. See you. Okay, so who can summarize the discussion here?
Well, basically, at least part of it is saying this algorithm will eventually use up all of the memory. Like it has a way to reach complete memory usage if you let it, if you need all that memory. But the more memory you use, the more likely you are to have to keep shifting things around, and the bigger they're going to be because that's what's using all the memory, and so you're shifting big things around by small amounts, which is expensive. And so long before you end up using up all the memory, you're probably spending all your time shifting things around, which is definitely something that happens on real computers. Like a C program never runs out of memory because the operating system gets tired of humoring it and kills it before it ever gets to that point.
So what does he propose? What are the possibilities of dealing with this inefficiency, especially as more and more memory is, as you're getting closer to full stacks, what could we do?
He says basically there are very few programs that will come close to filling memory without completely overflowing it. Undebugged programs will frequently overflow memory capacity, and undebugged is a sort of double negative way of saying bugged programs. To avoid wasting all this time, a possible suggestion would be to stop algorithm G if sum is less than S sub min, where S sub min is a number that you've chosen. So basically, if you start getting close, then assume you have a bug and kill it and let the programmer debug their code.
So your program starts to crawl, and it may take a long time before it finally dies. But yeah, just stop it from crawling if you can detect that. Yeah.
Yeah, actually, I would say that the crawling part is the most impactful one in the real life, right? Like, you might be still far from overflow, but your program is incredibly slow. So I guess that's even worse.
He's also saying that in real life, if you have 50% free memory, you won't have very much of these overflows once the algorithm stabilizes. So, but if you have more than that, you're going to have to do more and more of these shifting of the tables because you're going to get more overflows. And it grows exponentially, or as he said somewhere, as the square.
Yeah, that's the formula number 14, the average number of move operations.
That would be under a theoretical random, and when the pushes and pops from the stacks are randomly distributed, and that's not the real life case. You can have some stacks that are very active, some stacks that will push a lot of elements and then pop a lot of elements in a real program, and some stacks might not grow very much at all and not very often. And it could change over time. So that's why he's saying to make a model of how this algorithm would actually perform is really difficult, maybe impossible. But you do get a lot of feedback based on experience. I think in the Java world, you have this memory compaction problem, or these memory cycles, and they've improved memory collection algorithms each cycle. They do things like keeping the active memory in one heap, and things that objects that aren't being moved, they move from one place to another, so that they can do the memory scans for the free memory more easily. But what's happening in Java garbage collection is a little bit more complicated than even this.
Yeah, I think the intent here is for application level, sort of a custom allocator that you might have. These algorithms could be used for that level of memory management.
Well, at the application level, if I was programming in C, wouldn't I just use a separate malloc for each stack and let the system take care of it? I wouldn't try to do anything like this.
Yeah, I mean, I think, well, the entire book is showing its age, but, certainly this part is not directly applicable to programming. But it is what do we call it? Analysis of algorithms, for sure, right? We can definitely analyze this algorithm, even if it's something that we wouldn't actually do in real life. Right? I mean, if you actually have 4 arrays in memory that you're using as stacks, it is highly unlikely that you're going to code up this weird bumping, relocating them from here to here, right? Like, you're not going to do that.
Yeah, for most applications, I would agree. But as I mentioned, just that very simple pair of lists that are growing towards each other, that's used by sort. And I think any program that is either sensitive to the total amount of memory that it needs to use, or provides an option for that, would be interested in something like this. And there's definitely server-side concerns when you're running things on the server, where if you can say that my memory is bounded in some way, that could be pretty useful to know.
Do you have a link to the sort program that you're talking about? I mean, I assume it's closed sort.
If you just look up GNU sort, just search for GNU sort source. I don't remember where they keep the source for that. I think it's in bin utils. No, it's not bin utils, but core utils.
That's all right.
I think it's in GNU core utils. Yeah. But yeah, maybe I'll post a link to the actual file and the source. But yeah, and if you find any references, in case Arthur, you look for those papers that are mentioned at the end of the section, or somebody else, yeah, let us know, or mention it next time. So next time around, we're just continuing with the next section on next Saturday. There is a relatively long algorithm in there, so it's a bit more complicated and longer, definitely longer than what we just saw. It's the one on topological sort. I don't expect that we'll be able to do the algorithm and the program and discuss it really thoroughly. I'm just hoping that maybe we can get a sense of just the algorithm, and then depending on how much time we have, we'll look at the code as well. But yeah, so that's the plan. And yeah, so thank you very much for attending. See you guys next week.
See you. It was great.
Thank you, Zartaj.
Yeah.
Is that how you say your name, Zartaj? He's gone.
Yeah.
Zartaj?
It's pretty close. I pronounce it Zartaj.
Zartaj.
Yeah, so the second A is a little longer. And the first A is short.
Okay. Well, thanks for hosting it.
Thanks, Michael. See you.